So we're going to be talking today about some simple concepts that hopefully you're comfortable with already, and that's going to lead up to much more subtle things that are going to really challenge you when it comes to building real projects, which really are going to challenge you when it comes to the final exam. Things having to do with the Liskov substitution principle, proper use of subclassing, and creating effective subclassing, and preventing yourself from creating security risks through subclassing. Okay? So the next bunch of lectures are going to be squarely in the domain of how do you use object-oriented languages like Java, and any number of other languages, to build robust, easily modifiable, evolvable, and flexible, and secure systems. Okay, so we're going to be talking about the proper use of subclassing and subtyping, particular gotchas to watch out for. And we're also going to be talking about use of value objects, which are a very important building block when building scalable systems and larger systems that are robust, and preventing security issues. Okay, so as I said, hopefully everyone will leave this class with a sense that we're just going over and reinforcing some material you had before. So I've tried to emphasize in this class the central risk that we try to mitigate against in real-world projects, and that's the risk of change. Change that confronts us within software projects comes in many forms. Can anyone mention to me, when I say change, what do I mean? Give me an example of, if you're building a large software project in the real world, what are some changes you have to deal with? Yeah.
Change in requirements.
Change in requirements.
Whether it's client or whether it's automate, changes in how the world is working.
Okay, excellent. So one way there might be a requirements change is the user said, you know I told you to do it this way at first, but it's really clunky, and I came up with this better way I'd like to be able to get this job done. And I'd like you to build a system that will make that possible. Another issue is the client ends up having some underlying business change. So their company merges with another company, and suddenly you need to support compatibility with this whole other system. Another type of change might be that a new product comes out. Let's say you're working on doing development for handhelds 3 years ago, and then PhoneGap comes out. And now suddenly you have a better mechanism to address derived requirements. These are not end user requirements directly it's going to be addressing. The user may say, I want this running on Android and smartphones. And previously that meant, okay, we've got to go create an abstraction layer in our software, and we've got to then write things against that same interface from both the Android side and from the iOS side. And now suddenly you have something like PhoneGap, which allows you to do it more easily. And so the technology space changes. And this changes a lot. You get new technologies coming out every few years, which are disruptive. They eliminate sort of the need to engage in certain earlier technologies, and now you have a new set of derived requirements associated with use of these technologies, mastering them. Okay, and the change is going to afflict us all throughout software projects. And a lot of the big challenges associated with software engineering are protecting ourselves against this sort of change. When I say protection against change, what do I mean? Can anyone give an example that we're going to protect ourselves against this change? Anyone? What don't you want the change to have to entail? So there's a change, PhoneGap comes out, or there's a change that the client says, I now want your system running on Galaxy Gear smartwatches. Or, someone says, it's been an Android product and now I want it on iOS. What don't you want that to mean? Yeah.
You want to throw out the minimum amount of code.
Exactly. You don't want it to mean you have to rewrite the whole system, right? One small change leads you to have to go redo the entire system. It's like when you go and install something on your Windows box, you don't want to have to reinstall Windows with each, new application you install or something like that. And as we know, that's the reason I put that out there is because sometimes that does happen. Sometimes we reach the maximum beyond which our disk space is too small, and we have to go buy a new drive, and we have to install Windows on the new drive, and the old Windows we were using is not well supported, and so we have to upgrade to Windows, and it just cascades. So what you don't want is change to lead a small change in requirements, or even a modest change in requirements, to lead you to have to do a huge amount of work. You want to remain nimble. You want to be able to quickly adapt to those change needs when they come up. With minimal work, minimal time, you want to be able to just accommodate that change. Oh yeah, we built that flexibility in. Right? That happens. You say, oh, we already anticipated that, and we've got the flexibility to do that. So much of what we do, ladies and gentlemen, in software is about dealing with this risk of change. Software engineering is about dealing with the risk of change. We try to protect ourselves against possible likely changes. We can't anticipate everything. We can't be flexible in every sort of way. But we kind of will have some guesses as to where needs might entail changes down the road. And we try to make those changes as simple as possible. So that if we have this feature and we think another variant of it might be requested, we make that really easy to implement. 2 lines of code. Boom, done. What otherwise would require, weeks of work. So when we build software, one of the key ways in which we allow for change is a technique known as abstraction by specification. You need to modify kind of the business model, how things work within the system. Or if we need to modify the user interface, we don't have to totally gut the system. We don't have to go and throw out all of our, so suppose we need to modify the UI, we don't want to have to throw out all of our code that describes the basic rules by which the system operates. We don't want to have to throw out all the code that deals with the database. That should be more or less protected. So one of the keys here is we choose our abstraction. We choose kind of the mechanisms that we have in place, the fundamental building blocks, so that we can handle anticipated change as well. Okay, so we hide details of things that we anticipate changing frequently. We make just those small variants of each other, and if they change, no problem. It's just another variant of this small thing. We've generalized it so we can change it. Okay. Now, in Java, which both teams are working in, so I'm addressing it directly here. It's a language perhaps with which many of you are most familiar. We have 2 types of abstraction that goes on. We build methods. Rather than putting things in line, we call them methods, right? So instead of putting the algorithm for a square root in line, we create a method called square root. Maybe it even takes parameters. So it takes a value whose square root is to be taken, and it takes a tolerance level. So, and you can reuse it from multiple places. Trivial example. But maybe, in other cases you would display update method, and you call that from multiple places in the code, instead of putting that hard coding it in line in many different places. And this is a great thing. So, for example, we use functions or methods to provide functionality, to hide implementation details of what goes on, and we reuse those. We call them from multiple places. And they compute values, they do something, they change some state, okay? And that's great. And I will be pounding on this when I see code. Because if I see the same code multiple places, repeated, I'm going to be saying, why isn't this a method? Give me a method that does that. Instead of just repeating that code and then having to change all of those places in turn when something changes, wrap it up in a method. Wrap it up in a function, if you're in a language like C, or if you're a language like Scala, or what have you. Okay, so this is one type of abstraction. Another type that we'll be focusing on more in these lectures will be class-based abstraction or interface-based abstraction, okay? Here we're capturing, like in a class, state, the current situation of an object, the current values of it that it maintains, and behavior, so we can wrap up methods with it, okay? And we're going to be creating interfaces or classes that capture behavioral similarity between sets of objects. So we can just refer to an array directly, but sometimes we want to wrap that array up with some other information. Maybe it's the size of the array. Maybe it's what its initial value should be. Maybe it's other aspects of the situation. We can wrap that up in a class. And then we just call methods in the class. And the class does the work behind the scenes. And it knows whether it's in an array, or whether it's in a hash table, or whether it's in a hash map, or what have you. Okay. So we're going to be talking about uses of classes and how those classes implement contracts. They implement interfaces. Okay. So when we build classes like this, and in fact, when we build methods too. What we're trying to do, ladies and gentlemen, is to separate out. I'm trying to encapsulate some functionality. What that means is we want to hide some details of the system. So the persons using that method or using that class don't have to know all the details, all the gory details about how it's in. They just need to know what it does. If I give it this information, it will give me back that information. If I give it a tolerance and a number that's 0 or more, it will give me back a square root of that number that's within a certain tolerance of the true value. If I call this display update method, it will go and update the screen in the appropriate way and perform that operation for me. And I don't have to go look at that code of how it does it unless I for some reason need to think about changing it. Okay. So the idea here is to encapsulate some information and to specify that information in a contract. Specifies the what it does. And it's a contract because it says, if you give me this, I will do this for you. If you tell me this information that lets me get the job done and the information makes sense, then I'll go do a certain thing for you. I will take the square root of this number. I will update the screen. I will send this file off to the server to be stored and return an error code appropriately. Okay. So the idea here is that we're going to have these contracts, these agreements, these specifications, which are going to state basically what this code does rather than the how. You get that distinction? Look, software systems get really big. They get really big and they get ungainly. And typically we divide this up between many people, right? So each person here is going to have a different section of the code base that they're responsible for, or the testing code base, the set of tests. It's going to be a giant pain and going to get in the way of things if every person needs to know all the details of exactly how everything in the system works. You don't want to be in that situation. It will just be overwhelming. So instead, you let them do their job, trust that they've done it well, and all you need for them to tell you is what they need to do the job. So what their code does, and I don't want to know all the details of how it does. That's up to them. Okay? So here we're going to have a separation of contract, the interface, the standards, the agreements, the terms and conditions from the implementation, from how it's actually accomplished, the how. Separation of the what on the contract from the how it's actually done. Okay. When I say separation, I mean that for most people, they're going to be dealing with the what, just a few people who are going to need to worry about the details of the how. Okay? And by separating this out, it facilitates modularity. You can have a lot of people relying on your code without knowing all the gory details of how it works. And when you go and you change those details, they don't have to worry about it as long as you've maintained those guarantees. Does that make sense? Look, if you're going to ship, how many people in here have ever shipped something via the post office? Okay, good. Courier company, like FedEx, UPS, Later, anyone? Okay, just a few people. Okay. With the post office, right? It's a standardized interface. You know, we could invite someone in here, and for the next 10 lectures, they can be standing up where I'm standing here, and they can be giving a lecture on how the post office works. And you'd probably learn all sorts of interesting things. Be fascinating things about how it works. Do you know that 100 years ago they had like mail sorters who were actually on trains? As the trains would go across the country, they would actually sort the mail on the train. Sort it all out, so as soon as it arrived in the right city, it would be off and going. So there, like, major post offices were going on trains. And today, you know, there's all sorts of interesting. Someone told me a lot of Saskatoon's postal workers actually get driven in taxis to where their location. I don't know for a fact that's the case, but I was assured that it is. That all the taxis converge in the post office in the morning, and they fan out across the city. So we learn all sorts of interesting stuff. But who has time for that here to, you know, learn all the details of post office? Look, you want to get a letter to Halifax, you want to get a letter to Ottawa or whatever. You want a simple contract in place. You want to know, I put a stamp like this on this letter and it will get there. Put a stamp in this letter, write an address, write a return address, stick it in a postal slot, and it will be gone. You don't want to know all the details of the post office. There's a separation here of the interface, which involves a stamp and some rules about what you have to write on this letter, from the implementation, which is incredibly complex and probably involves, you know, sometimes sending it via a truck. If you're sending a letter to Tisdale, you know, they'll deliver it on a truck. If you're sending a letter to Ottawa, it'll be delivered on a plane. And if you're sending it to China, it'll probably be delivered on a plane as well and have to go through customs. That's the implementation details. What you just need to know is how much do I have to put on the letter, what do I have to write on it. That's the standardized interface. Separating out implementation from interface is key to avoid just overloading people, to allow them to focus on their particular areas of life without worrying about how everything in the world works. Okay? So this is a general principle we apply in many areas of specialization in life. And what it depends on, ladies and gentlemen, it's either implicit or explicit specifications that indicate the what. That indicate the expected behavior provided in the interface. So I need to know something about what the what is guaranteed if I put a stamp on my letter and I send it off. Or if I pay FedEx $25 to deliver this thing to Ottawa, I want to know certain things about what's to be expected. What can I count on? What sort of things might FedEx tell me that I could count on? If I pay them whatever it is, $30 to deliver something to Ottawa, what sort of things might they guarantee? Number of business days. How soon it's going to get there. Is this good? So if I go and I drop something off at 10 a.m., is it guaranteed to get there by the same day, 5 p.m.? Is it guaranteed to get there by the next day, 5 p.m., or by 5 p.m. 3 days from then? That's a key thing. Another part of the interface is money. You know, how much do I have to pay them, right? Another part of the interface is maybe some guarantee that it will be delivered in an intact fashion, right? So if you ship off a computer, it doesn't end up in a smushed mess or something like that. They provide some guarantee. So there's specifications. There's terms of reference that I can look up that will say, okay, for this rate, for this amount of money, you get this level of quality of service. You get this timing guaranteed. Okay, so we do this in life all the time. We want to know what is promised, and we let them take care of the how, right? So this is, many areas of human activity, and I think I have, examples with us here, right? We buy our bus passes, or you get your bus pass anywhere, and you can take a bus anywhere, right? You go to Toronto, you can take this transit, no matter where you happen to buy the transit pass, you can use it anywhere throughout the system. So protocols are the same way. It doesn't matter TCP IP, it doesn't matter whether you're doing it from a PC or from a Mac, as long as they basically speak the same bits, it knows what to do with them. So we separate interface from implementation. We let some other people take care of the implementation, and we just go through the interface, or we take care of the implementation and they go through the interface. So when it comes to computational stuff, when it comes to software code, this is the sort of interface that I have in mind. This is the sort of contract I have in mind. So this is from Liskov and Gutek's book on abstraction and specification and object-oriented design, and specifically focused on Java. It's a great book. I'd recommend to anyone. It lays out the ideas behind this in beautiful detail. But the idea here is, like, we have an inset, there's some overview, it says insets are mutable, unbounded sets of integers, and they figure out how to describe how to denote it there. And then they have various methods. And there's a constructor, which says it initializes it to be an empty set. There's an insert. It modifies the set by allowing you to add this element that specifies the element. Removes extra. Okay? So this is a specification. What is missing here, ladies and gentlemen? I said it's a specification. I didn't say it's a full class. What's missing here right now? Yeah, an implementation. It's true that we could indicate this in Java.util fashion. That might be a good way to do it. But a key thing that's missing in terms of my description is, for me to look at this and understand it, understand what I'm promised, I don't actually have to look at exactly how it maintains its data structure. Does it use an array? Does it use a binary tree? Does it use a hash table? Does it use some other sort of dictionary? I don't need to worry about this. I know what this is guaranteeing, and so I could actually use this based on this rather than going and looking at all the code. And this is easier than looking at the code. You may be a really bright programmer, but do you really want to be spending all your day looking at other people's code just to figure out what is guaranteed by it, what you can count on? Probably don't. You don't have time for that. You have to write your own code. If you can get a high-level understanding about what's guaranteed, what is ensured, what you can count on from an interface, that often gives you everything you need to know to use elements of type int set. So if I have an int set, I know what I can do with it. Does that make sense? Does that make sense? So the idea would be, here we have this specification. Now, ladies and gentlemen, the truth is, it takes some thinking to put in this sort of specification. Modifies clauses, effects clauses. What is actually changed? What's the nature of those changes? Any return values that are going to be specified, right? So, for example, the size, the effects here, returning, the size of the set. It takes some time to specify this. And I would love it if for your code you have these sort of descriptions in them. What happens if you don't? Well, sometimes you just put a bit of comments above this, removes an element or something like that. And that provides some information. Hey, it's better than nothing. If you don't have anything at all, what do people turn to? Most of us didn't have these modifiers and effects. Didn't have any of that stuff. What would people turn to? How would they make sense of what this is? Yes, based on what the name is a lot of it. Let's get back to the issue of why naming is so important. Naming is one of the most important things you have control over and that people turn to get an understanding of what your code does. Absolutely key. Okay? And if you don't, especially if you don't have these sort of specifications, I'd urge you to put these specifications. It'd be great. Fantastic. I would love it. I would reward it. But if you don't, at least think very carefully about the names. Let's suppose the names are lousy. Let's suppose the names are not clear. Let's suppose it's not obvious. What do people turn to then, if they can't? Code. And that's where it starts getting messy. Why is that bad? After all, we live in this world with lots of open source code systems. We can download code for all sorts of areas of functionality. We're using graphics libraries. Often we're using open source graphics libraries. We can download the code. Why isn't that enough? Why isn't that enough? Why doesn't that solve the problem? Great. So often the code is hard to understand, particularly for more sophisticated code, which involves complicated algorithms, fancy data structure, trying to figure that out, what the intention behind it, what it means, what it does at a high level from the code is hard. It's really hard. So that's one big vulnerability. Spend a lot of time doing it, and you may come away with the wrong impression, right? So that's one thing. What's another problem with looking at the code? Suppose that you could go there and you're a hotshot and you can figure out what it means, how that code works, right? You can sort of reason through it and you have some sense. Why is that not enough? Okay, exactly. So you may be counting on arbitrary things in that code. That code may have all sorts of things in it. You know, how it handles special cases, what data structures it uses, and exact details of how it works. And you may come to count on those things, right? You may come to rely on them in a way that the person who wrote the code can guarantee. And guess what, folks? You're not the only people in the world who has to deal with changes. They have to deal with changes. Whoever wrote this code will probably have that code evolving over time. And guess what? If you're depending on vague details, vagaries of how it's going about its business, those may change over time. Maybe they go from depending on an array at first, to implement a bit vector, to depending on some new bit vector class that they got from Apache or something like that. And suddenly your code no longer works for there. It's broken what you're counting on. You were counting on them doing it in a certain way, and now and they didn't mean to guarantee that. That was not in their intention to promise that it will always handle from now on null values that you pass in. And now your code breaks because they changed the inner implementation of there. Ladies and gentlemen, that's a recipe for disaster. If your code depends on the vagaries of everyone else's code, that's just cruising for bruising. It's a disaster. It's a disaster because now everything is coupled. Everything is coupled together. You change one thing here, it could lead to breaking all across the world. It'll be as if, just because, maybe you've been counting on Joe working at the post office, that Joe delivers by bike on his way home, mail to the certain address. If you had to depend whether or not Joe bikes home from work, whether your letter would be delivered on time or not, you're in bad way. Because Joe might not want it. Maybe he'll retire. Maybe he goes into the hospital and he's not available. Maybe he can't ride his bike home anymore. And now suddenly you're not unable to deliver a letter. You can't have a viable, scalable system which depends on the vagaries of how things are implemented everywhere else. Your code should be depending on things that are guaranteed by other people's code. Depending on what their code does, not all the details of how. And then, if they have to change something, it's no problem if it's not something they've guaranteed. If it is something they've guaranteed, they know they have to stick with it. Right? So if you had no guarantees from FedEx, you just need to know, who works for them and what particular plane flies in and explain is, you know, your life would just be a mess because you couldn't count with confidence on certain high-level guarantees, and your ability to sort of function will be severely impaired. Instead, we want to count on guarantees, things that no matter how this int set is implemented in the future, it will live by these guarantees. And they may have all sorts of fancy, fast, clever ways of doing this in the future, of implementing this. But as long as it makes these guarantees, our code won't break. Does that make sense to people? We don't want our code to break based on minor modifications of other people's code. The final thing I want to say, and these are testable, waiting to be tested. Waiting is the primary reason you don't want to depend on other people's code is because sometimes, ladies and gentlemen, that code is not available. How many people here have gone in detail through the code implementing Java's object class? No? 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 Well, guess what, folks? There's a lot of code that, even if we have access to someone else's code, we don't have access to the code that depends on, right? There's all sorts of third-party libraries out there which we'll have in jar files, and we don't have access to the code. Even if we wanted to, we wouldn't have access. Okay, so, ladies and gentlemen, we try to encapsulate things. We try to separate out the interface, what is promised, from the implementation, how it actually is accomplished. Why do we do this? Well, we have a separation of the implementation that leads to locality. We can build one piece of the system without worrying of modifying another. Modifiability, we can change one piece without breaking other code. We can change our internal implementation. We can change what data structures we use without worries that suddenly all sorts of people's code is going to break. If we haven't changed what we're promising, we can do this safely. Substitutability. We can replace one implementation by another, as long as it maintains the same interface. Maybe we're used to going to FedEx here in town. And just because the FedEx franchise now is owned by Jane instead of by John before, it hasn't changed our ability to count on FedEx hours, count on when we have to deliver something for it to be guaranteed to be across the country in 2 days or what have you. We can substitute one for the other, right? And we can reuse. So for example, we can have two implementations that differ only with respect to the types involved. We can have a generic type that implements both. Okay, so in defining this interface, something like this, ladies and gentlemen, we're seeking a sort of contract, and we do it by specifying these specifications. Okay. Now, in Java, there's two fundamental ways of defining these interfaces, these contracts, that allow us to encapsulate, give one set of promises to the outside world while still allowing us to modify things. So we can use an interface in Java, an interface construct. How many people here have gone and implemented their own interface in Java before? Just as a sample. Okay, virtually. Good. Good. So you're comfortable with this. What's the difference between an interface and a class? What's one big difference? What does an interface not have in it that a class commonly has? Doesn't have an implementation. Just has identification of mechanisms, particularly methods, whose signature has to be defined by any class that implements that interface, right? So you have a class C, and it implements collect, or it implements writable, or whatever. Okay. So here the interface defines the specification of the contract, and it's a great place to put those sort of modifies, effects clauses, or preconditions, postconditions, invariants, etc. And there's no implementation. And any number of classes could implement this interface. Beautiful separation of interface from the. Okay. classes provide an interface, but they provide it with an implementation. They have implementation with them. They have code in there which implements the interface. And generally, in many languages, we can see the class without seeing the code. Give me a language where we commonly will see a class definition without actually seeing directly the implementation of that class. C and C++. With classes C++, we have a .h file which specifies a class, the methods in that class, and then we'll have a .cpp file, for example, which specifies the code for each of those methods, right? And often in C++ projects, we will distribute the .h files widely, but maybe only we have access to the .cpp files, the person who created it, right? You've seen that before, yeah. So you distribute a .object file, a .o file, which is the code, and you have a .h file which goes along with that and which describes the interface. So this is good, but it bears noting that conceptually, classes in Java provide both implementation and interface. So if I got a .jar file, and I use autocomplete in my .jar with that .jar file, I have some object O, a class, class I have. Autocompletion knows about the methods of that class, right? I say O dot in a control space or whatever, it will fill it out, right? So fill out the various names if possible. That's information from the interface. And often it will provide JavaDoc along with it that specifies what it does, right? So here we have the separation of interface, which is what I might see in autocomplete, from the actual, all the code for it. Okay. So if a class C implements in Java, an interface, we say implements, and then implementing an interface allows one to deal with that class through that particular interface. So if we say this class implements collection, then people can treat this class, an instance of this class, as if it's a what? As if it's a collection, right? And a given class can implement how many interfaces? Many. You could have this, your given class implement 10, you can implement 1, you could implement 100 interfaces. And you could treat it as if it's any one of those interfaces. It's a writable, it's a serializable, it's a, it's a collection, it's a mechanism for time stamping, what have you. You could have any number of interfaces and the class implements that. So we could have one implementation and many interfaces. So this is true in the real world too. Look at machines here. A computer implements many acoustic standards. It's guaranteed that that computer is not going to make me deaf. It's going to be held to a certain decibel level. So when I was flying back at 1 a.m. yesterday, 1 a.m. today, I wasn't driven deaf in the plane, and others weren't driven deaf. It has electromagnetic radiation standards, usability standards, keyboard layout, power consumption. There's different aspects of this computer that are guaranteed by different standards, different interfaces. And similarly, a car has certain fuel economy, etc. Okay, knowing what is promised in a given area here. These are all about promises, right? These are all about guarantees that this system will adhere to. It has a certain acoustic profile, it has a certain energy profile, it has a certain usability certain keyboard profile, etc. These are guarantees that this computer will adhere to. Car similarly has certain safety standards, acoustic, fuel economy, vehicle width and height standards, so it'll fit onto a normal road, etc. Okay. So knowing what's promised in a given area allows us to deal with assurance about this artifact, even if the exact details of the artifact remains unknown. So we may have something like this, where class X implements these two different interfaces, each of which guarantees certain things. It has a contract. Does that make sense? Yeah? Okay. And you can imagine a store here in town that simultaneously serves as a shipping point for UPS and for FedEx. Either one. It's compatible with it. You go in there to the vet and you ship it out for FedEx guidelines. Maybe you get it there by 10 a.m. It's guaranteed to be in Ottawa by 5 p.m. the next day. If you go in there for UPS, it's a different pricing point, and they'll have different delivery options, right? Okay, so these are familiar things from daily life. Okay, let's talk about subtyping, and this will start to get key for next time. This hopefully is foundational stuff. But I'm just surprised repeatedly in this class by this failure to separate interface from implementation, the failure to realize the importance of encapsulating. So I'm hoping some of this will sink in. But the most pressing need for this will be next time when we talk about the Bliss-Scope substitution principle, which has to do with subtyping and safe subtyping. So what does subtyping mean? Does anyone, that may be a term less familiar to you. If I say this class, an array is a subtype of a collection, what does that mean?
That means that the array has properties of the collection, but it also contains some properties.
Okay, so there are certain properties, certain guarantees that are ensured by any collection, and an array may have lots of other properties, but it has to adhere to those guarantees. If we're expecting a collection, we should have all of our expectations met by an array. But it may have lots of other things that it ensures as well. Right? It ensures that things are in a certain order, or what have you. Yeah. So a subtype must be in some sense compatible with its supertype. Okay. When I say compatible here, I mean in terms of how it behaves. It needs to behave in a way that's compatible with its supertype. And we'll get into the details of this tomorrow. If we're expecting so if we have an A that's a subtype of type B, so if we have an array, it's a subtype of collection, and we're expecting a collection, we should not be surprised by the behavior of an array. It should behave in a way that's compatible with being a collection. We should be able to frob it as we would with any collection. Let me give a real world example for this. And this is gonna come home next time more. Okay, so suppose that your name is Fred. Suspend disbelief for a certain amount of time. And you want to set up your own chain of FedEx franchises. You're going to call them FredX. Okay? And you're really good at managing these things. So you're actually going to have several of them. It's not just going to be FredX. You're going to have FredXs. And they're going to be really familiar with dealing with FedEx. Okay? And so you're going to have these FredXs around, and originally they're going to start in Saskatoon, and they're going to expand out to other municipalities. Now, for this to be a legitimate FedEx, you have to adhere to all the terms that a FedEx guarantees. So if someone goes to the FedEx website and they say, what time do I have to get my package for it to be in Ottawa or tomorrow at 5 or tomorrow night in Ottawa? It has to be there for a wedding tomorrow night in Ottawa. It's the bouquet for the group, for the bride or whatever. So what do I need to do to get it there? They go to the FedEx website and they see, okay, it has to be in by 10 a.m. to a FedEx outlet. Okay, fine. previous day. So then I go and I say, what's the nearest FedEx outlet? And I find one of these FedExes. It's a FedEx, right? It's a FedEx. And so I go to that FedEx, which happens to be a FedEx as well, right? Now, I'm walking into that FedEx, and I'm going to drop off this bouquet for the wedding tomorrow night. And when I drop off that bouquet there, before 10 a.m., I'm counting on them adhering to the FedEx guarantees, right? I'm counting that I'm going to pay this money, put that on those smackers, and I'm counting that by tomorrow evening, that's going to be at that wedding in Ottawa. Why? Because they're a FedEx. They're not just a FredEx. They don't just have this really nice guy, Fred, who's dealing with me. They're also making the guarantees of being a FedEx. So whatever the money sides are, they're not going to charge me more than FedEx, or they're going to be guaranteeing at least the time guarantees that FedEx does, right? Would it be okay, ladies and gentlemen, if this FedEx said, we'll get it to Ottawa, not just tomorrow at 5 p.m., we'll get it to Ottawa tomorrow at noon. Would that be okay? Wow. Wow. Man, Fred, you're good. Now, would it be okay if they said, well, Johnny's driving our truck, and he has to go to baseball practice tomorrow, and so he's not going to be available. So, we can't do 5 p.m. tomorrow in Ottawa. We can do 10 p.m. tomorrow. Would that be okay? No, they're not adhering to the FedEx rules. You'd say, you're not a FedEx. You're a fraud, Fred. Right? You can't hang a shingle saying you're a FedEx outlet, and then you don't adhere to the FedEx constraint. You can do better than the FedEx guarantees, but that's still living within them. You can do even better. But I don't want to have to know about that your driver's named Johnny and he has a baseball practice, but it might be rained out tomorrow, in which case there won't be a problem. And I don't want to have to know all those details. That's your business, Fred. That's your business. I'm paying you as a FedEx to get this thing delivered. I'm dropping off by FedEx rules before 10 a.m. and it's your business, whether it's with Johnny or Joe or Sammy, or whether someone has to go over to the airport on roller skates. That's your business. You take care of that. I'll take care of my business. That's what I want. I want that contract that they adhere to as FedEx, right? And if they don't adhere to it, it's a fraud. Because they're not actually a FedEx. They're not compatible with the FedEx. So I may be counting on all these aspects of FedEx by virtue of them being a FedEx, but they may have other properties too. Maybe they give me a big bow back, or maybe they send me notifications as soon as it's arrived, or maybe they let me track it on my iPhone and the Fred app that perhaps one of you will go on and write. To actually track it across the country, or maybe they'll give me every time I ship off a package, they'll give me a framed photo of Fred that I can hang in my classroom. FedEx may make certain guarantees. FedEx has to live up to at least those guarantees, but they may provide more features, right? So they could provide more strict rules, but they've got to live up to this, okay? So when it comes to subtyping, if they say we're a FedEx, what it means is that the promises that they make, this is absolutely key, folks, and this is going to be a differentiator of the next few lectures. The promises made by FedEx need to be compatible with the promises made by FedEx, right? Does it say that FedEx will even be guaranteed to use the FedEx planes? No, it doesn't say that. That's their business. Whether they use the FedEx planes or whether they have, Johnny Rocket flying on a rocket of his own to Ottawa, that's their business. But what it does say is that they must promise things that are compatible with FedEx. Does that make sense? So subtyping is about promises, folks. It's about what's promised by the franchise. How they actually go about it, that's their business. That is not an issue of subtyping. That would be an issue of subtyping. It is not an issue of subtyping. Subtyping is about promises. But what I can count on, the specifications, the contracts, okay? Now, in general, we're going to create subtype hierarchies. So we might have, in a medical sense, we might have health professionals who are persons, doctors who are health professionals. And in Java, we have things like this. So all sorted sets implement the set interface. To some extent, sets, and it must adhere to the guarantees of sets. Sets are termed collections, and all collections are termed iterables. Right? Similarly, queues are collections. A sorted set is not a queue, but all queues are also collections, and all lists are collections. Right? So we have these subtype hierarchies, and they're defined by their contracts, by their promises. I know with it being an iterable, I can use it in a L, two O's, and a P. Thank you. So, you know the story behind me in the L, two O's, and a P? Folks know that? I think I was in 5th grade, and I wore younger man's shoes at the time. This is just in the advent of computers. I was programming in assembly language. But this is on little calculators. I really wanted to use a computer, so I went and I signed up for an adult education class involving computers at our local high school, and it was great. I got to go there, and I was on these various systems doing a bit of programming and so on. And then the professor said something which shocked me. He said, "We're going to have an exam." Oh man! And he had gone through. I hadn't really paid much attention. I hadn't paid that much attention to his lectures, but he said, "We're going to have a review session." So that was my hope. So he was going back and forth, walking back and forth, going over reviews. And he was saying, how would you, if you wanted your code to do something different, if A was larger than 5 or less than or equal to 5, what sort of statement would you use? An if statement. That's right. And then he was walking and said, suppose we wanted it to go through numbers from 1 to 100, one after the other, and do some for each of them. What would we use? And he stopped in front of my desk and looked at me. He said, what would we use? I looked up. And he said, I'll give you a hint. It has an L, 2 O's, and a P. Cool. True story. Anyway, so in this case, we can use iterables in loops. Pools are not quite ready yet, but loops, we can use them in loops, and we can iterate through them. They're guaranteed to. The loop interface counts on having that ability to iterate through them, and we can call certain things like the next to get the next element on an iterable, etc. Collections have additional methods, and a sorted set is guaranteed to support all of the functionality, all the guarantees, all the promises, all the contracts associated with a set, associated with a collection, associated with an iterable. But it has other features as well. Does this make sense to people? Okay, so this is all about type hierarchies. There's another type hierarchy, writers and readers and objects, etc. Okay, now, I want to talk just briefly about it and try to stir up a bit of appreciation for next time about the distinction between, and actually this is going to be for 3 times from now, with subclass. So if we subclass one class on one, so class A is a subclass of class B, how is that different from subtyping? well, actually, sorry. Maybe before I say this, there's another feature that comes out of these type hierarchies. The fact that I can treat a sorted set like a set, and I can treat a set like a collection, and that like an iterable. That allows me to treat a sorted set, for example, as an iterable, right? Okay, what does that allow me? What's one of the most powerful ways I can use that in Java? It's a long word. It begins with a P. It ends with an M. It has Greek origins. Polymorphism. What does that mean? Or, roughly speaking, what would you say that means?
You can call the same method and method.
Yeah, you could pass. So this method may expect an iterable pass to it, right? And you could pass it something that secretly is a sorted set, right? Maybe it's a tree set, for example. Or I could pass it a linked hash set, or I could pass it a priority queue. And I could reuse that same code calling off to this method with all these different particular things, an array list, a priority queue. I could pass those off. As long as they're all intervals, it's all fine. That same code can be reused for many particular classes here, as long as they implement the requisite interface. Does that make sense? Polymorphism, one of the most powerful ways we can use this sort of subtyping. You know, why is that possible? Because if it's only counting on properties of this being an iterable, after all, any priority queue is a queue which provides all of the guarantees of a queue, all the guarantees of a collection, all the guarantees of an iterable. So it's fine to pass it in. It's an iterable after all. There's lots of other things secretly associated with it if I knew that it was a priority queue. But from the point of view of this function I'm calling, perhaps all it cares about is that it's an iterable. That's all it counts on. And it can do its work based on those guarantees. Does that make sense? Yeah, this has huge implications, because you can write your code. You can write your code with separate things to handle priority queues, and linked lists, and array lists, and linked hash sets, and tree sets. And you can do that till the cows come home. But it'll be much more effective if you could all do it just counting on it only being an iterable. You can reuse that one piece of code. You don't have to write it for all those particular classes. So polymorphism is very powerful. Ladies and gentlemen, how is subclassing different from the subtyping that we have here? So I've been talking about subtyping, which is all about the promises. What is subclassing? How does that differ? So if I say A is a subtype, is a subclass of B, how is that different? Let me ask this. If I say A is a subclass of B, can I pass around an A as if it's a B? The answer is yeah. And Java will allow me to do that. If I say A is a subclass of B, if I say, this class, it extends a hash table, I can pass it around as a hash table, right? Right? Polymorphism? Okay. So that's true. But what else does that give me besides the ability to just pass it around polymorphically? Okay. So you're getting to the key issue. So that subclass, what does it get for subclassing? It gets the ability to be passed around, but it also gets methods and properties. It gets the implementation of that class that it's subclassed. So it gets the implementation of the hash table. So that hash table might have lots of internal details, lots of specific details to implement a hash table. And we're not even only saying that we're a legitimate hash table, that we're compatible in our promises with the hash table. We're actually saying, hey, give me all of those mechanisms in me for my class, the subclass. I want all of those mechanisms in my subclass, okay? So subtyping concerns what is promised. Subclassing is concerned with how this is accomplished. It actually reuses the implementation. And that's why I can't say this extends, this class extends a collection. It implements the collection, but it doesn't extend it. There's no reuse of implementation. So with subclassing, I'm actually reusing the implementation. Okay. Now, it turns out that this sounds great, but it also comes with some big dangers. Okay. It comes with some giant dangers. One of the biggest dangers, we're going to be talking about last time, is I said that if A is a subclass of B, can I pass around A as if it's a B? Yes. Java compiler will be say, yes, sir. And it will just allow you to pass around. But ladies and gentlemen, this is the troubling thing. In order for A to be legitimately passed around as if it's B, it needs to be a what of B? It needs to be a legitimate subtype. It actually needs to be compatible with all the promises. And guess what, folks? Your compiler is not going to be able to check that. Who's going to check that? Who's responsible for checking that? You folks. And this is a giant problem with object-oriented programming. This is caused behind quite a few bugs. They declare A as a subclass of B, but it's not a truly compatible with B's promises. And it breaks. And some of the code that's counting on it being a B will fail, in which case you've got a bug. The Java compiler will say, yes, sir, pass it around. Assumes that it's legitimate, and it's not necessarily. And that's what we're going to be talking about next time, and that has to do with what's called the list of substitution principle. That A is declared as a subclass because you want the goodness, what a former student Dave Bushnell would call the chocolatey goodness of subclass. You want to be able to reuse those mechanisms, that implementation. You want all of that for free, but you're not willing to adhere to those same promises. You're setting yourself up for a fall. So subclassing brings two things. It brings subtyping and it brings code reuse via implementation inheritance. We say it inherits the implementation. And ladies and gentlemen, this gets tricky. You need to be absolutely sure that that subclass is indeed a legitimate subtype, that it's compatible with, that it lives by the same guarantees as the superclass. So it would be as if fredx said, we're a FedEx, and guess what? We want to use all the FedEx mechanisms. We use all the FedEx planes, all the FedEx trucks, and all those sort of mechanisms. But guess what? For us, you have to get your package in by 8 a.m. to get there to Ottawa by 5 p.m. the next day. And someone walks in, 9:45, having counted on the FedEx guarantees on the website, say, here's my package, and they say, oh, well, that won't get there for 3 days. You got to pony up more money if you want it to get there by tomorrow at 5 p.m. And the person will say, well, wait a minute, I checked on the FedEx website, and it says this is guaranteed. They say, well, for FedEx. And here they're using all the FedEx mechanisms, but they're not living up to the promises. That, ladies and gentlemen, is where the FedEx is a fraud, and that's where your classes can be a fraud. Your classes can be fraudulent. And I'll be looking for those in your code, because they're very common. People use subclassing to reuse mechanism, to inherit, to reuse the implementation as a convenience, but they're not willing to live up to the promises, and it leads to bugs. And it leads to bugs being proliferating within the code. So here, as I said, to be a valid FredX franchise, you have to live up to the same terms. You could be FredX, and people will be perfectly happy with you being a FedEx franchise from the point of view of customers if you made use of your own mechanisms, if if you made use of your own planes, your own IT system, as long as you guarantee, FedEx guarantees, as far as they're concerned, they're happy with you as a FedEx outline. And that would be like a subtyping of FedEx. It's like I'm providing all the FedEx guarantees, and I'm not gonna use their mechanisms. I'll use my own mechanisms. You know, I have really fast horses to bring down the suburbs of Saskatoon and so on. And that's fine. If you can do it, if you can live by those guarantees, power to you. A subclass would say, okay, we're going to be reusing all the FedEx mechanisms, all the FedEx planes, and so on. And if you're doing that, you still have to adhere to those FedEx promises, or you're a fraudulent. You're like fraudulent Fred. Okay? Okay, so just a few points in closing here. Subtyping is about the what. It's about promises and guarantees. Whether it's a subtype or not is an issue of whether the promise is in some sense compatible with those of the supertype. If it's a legitimate one, it can be substituted perfectly without problems for any case where the supertype would be needed. And it lives up to those promises of the supertype. Subclassing is not only about the what is guaranteed, but about the how, the implementation. And it carries with it implications of subtype, but it also builds atop the implementation. Finally, subclassing implies subtyping, but subtyping does not imply subclass. You can have a subtype without reusing the mechanism, without reusing the implementation. Okay? If A is a subclass of B, if A is a subclass of B, A is a subtype of B, but the vice versa is not the case. Okay? So we're going to build on this next time to look at the Liskov substitution principle and see how to prevent yourself from tripping up on it, like so many people have within the object-oriented area. Okay? That's good. One final thing I'll just mention, Dylan, TA, will be here he'll be coming here for the tutorial, just to see if there's any ways that he might be able to interface through your teams, clarify any issues, talk with you about your situation. So if you'd like to meet with him, I suggest that both teams be here, or we could talk with each of you. So that would be 4 p.m. today. If you want to then go meet over in Sphinx or whatever that we want, I would just suggest that you start the tutorial time here. Okay? That's all for today. And if Josh, if you or someone in your team could come up and help me